Now let's look a bit more into how to ventilate or to cool electrical machines which are encountering a heating phenomenon. Now, as the size increases, the temperature rise increases at a higher rate than the surface area is capable of cooling it. So that means that for this kind of machines, you would need external means of cooling, additional means of cooling apart from the natural means of cooling that is present. So let's look at the means by which we can cool machines. So first off, we have those machines that can naturally be able to cool themselves. These are usually small machines that do not require any special cooling. So no special cooling parts. Simply their surface area is sufficient for the cooling mechanism. Number two, you have self-cooling machines. These are the types of machines which the fan, they have a fan mounted directly onto the shaft. So obviously this only applies to rotational machines. Machines like transformers cannot make use of this kind of cooling system. And finally, you have separately cooled machines. And these make use of a variety of different types of cooling systems. You can have open circuit cooling systems. This is whereby you have ventilation, whether forced or otherwise. Forced meaning you have fans that are included, and these are either induced cooling mechanisms whereby the flow of air is outward. So outward flow of air. You can think of it that the fan is sucking out air from inside the machine, or you can have forced ventilation whereby the flow is into the machine. Fans blow air into the machine. You can also have closed circuit machines, closed circuit cooling, whereby you have you have fans that retain whereby you have gas that is circulated between the machine and a cooler. And then you have surface ventilated machines whereby the cooling medium comes into contact with the machine. Right? Closed circuit, we have medium circulates between machine and cooler, right? So in order to accommodate all these different types of cooling mechanisms, you have a series of enclosures that you can make use of to further classify these machines. And so these are the types of enclosures that we can make use of. So right up here, you have the open type of machine, whereby you have either they're mounted on the bed plate or they're mounted on the end shield. Either the machine is fully open to the elements and has no sealing or enclosure that prevents ingress of materials. Or you can have various levels of protected machines, either deep proof, splash proof, or hose proof, especially in areas where you would want to, for example, wash the machine. Hose proof is a useful type of ventilation. Then you have pipe ventilated, whereby you have pipes that are built into the machine itself, whether they are pipes or ducts. You can have forced or induced, whereby we said forced, the flow is inside, induced, the flow is outward. Then, of course, you have totally enclosed machines. These are fully enclosed, and you have circulation of cooling media within the machine itself. And in this case, where you have totally enclosed, you can have either a primary coolant, which is a gas or air or water or oil, hydrogen, nitrogen, any coolant, any liquid or gas that is circulated within the machine and draws out the air directly from the machine, draws out the heat directly draws out heat, draws out heat from the machine. But you can have some systems where you also have a secondary coolant, whereby you have the primary coolant that comes into contact with the machine directly, and it is passed through a heat exchanger, where the heat exchanger now contains a secondary coolant that in turn takes the heat from the primary coolant out into the environment. So the secondary coolant is a medium at lower temperature, than the primary coolant. Right? Okay. So now let's look at the process of actual heat dissipation from machines. So now this is given by the formula indicated below. So we have Q is equal to Wm times Cp times theta, whereby this is heat dissipated and Wm is the weight of the cooling medium as it is applied to the machine per second. Right? Then you have Cp, which is a specific heat of the cooling medium. And of course you have theta, which was temperature rise. Okay. Temperature rise. So this is the formula that explains when you have a ventilating medium, or you have any medium that is used in cooling a machine, how does the medium dissipate heat? How does it take the heat from the machine and pass it on to the ambient environment at a lower temperature, thus bringing the temperature of the machine down? This explains that process. Heat is dissipated in kilowatts, so you have to take into consideration time when you're doing this, because as the machine is operating, it is continuously generating heat, as we described in the previous section. So the time has to be put into consideration. It is energy per unit time, and this is measured in kilowatts. The weight of the cooling medium is the number of kilograms that you can pass over the machine per second. Remember, time still has to be taken into consideration. So if it is a gas or a liquid, how much of that gas or liquid can pass over the surface of the machine in order to take away the heat from the machine itself towards the environment and thus drop the temperature. You also have the specific heat of the cooling medium. So what is the capacity of the cooling medium to absorb heat? And this is the specific heat, and it is described in that way. So it is kilowatt seconds per kilogram degrees Celsius, right? The number of watt seconds that it can dissipate for every kilogram that it passes over the machine, and for every degree of temperature that it enables to drop. Next, you have temperature rise, which of course is in degrees Celsius, right? Now, this formula has a special case whereby in the case of gases, in the case of gases, you then have an additional requirement that you will generally be measuring the volume of gas or the volume of air that you pass over the surface. So you will then have a special version of this, which is volume of air per second over the volume per kg of the gas, right? So this, if you resolve the dimensions, it will come back to these dimensions that you have here. So if you resolve the dimensions, they will look like that, because it is meters cubed, which will cancel out, so you'll end up with kilograms per second. But in the case of gases, it is usually easier to take it in terms of volumes per second. Right? So now let's look at an example with which we can better understand this process. So let's find the amount of cooling air required per second at the inlet temperature of 25 degrees for a 25 MVA alternator with that efficiency, and these are the constants that we have. Okay, so to start with, we need to calculate the losses that are being generated in kilowatts. So every second, how much energy is being contributed to, or rather is contributing to the heating of the machine. If you look at, we are given the kVA as 25 MVA. This is at a power factor of 0.87. So you will then have 25,000 times 0.87. If we bring out the calculator, we will then have 25,000 times 0.87, which gives us 21,750 kilowatts, right? Those are our losses. Now we know that the loss, this is our output. We know that our output is 96% of input, and that the losses are 4% of input. This means that if we want to get our losses, we can get 21,750 divided by 0.96, which is 96% of input, so that you get the input, times 4% of that. So this is the input, then 4% of that will be 0.04. So 21,750 times 0.04 divided by 0.96, and that gives us, it comes to 906.25 kilowatts. Okay. Next, we try to find, we know the temperature rise that has been indicated. So from ambient of 25 degrees, temperature rise will be 50 minus 25, which is 25 degrees Celsius. And our specific heat is known. It is 0.993 The units we said were kWs over kg degrees Celsius, right? So we have all the requirements for our equation. Zoom out a bit. Right? We have all the requirements for the equation right there. We have the heat dissipated, which is the amount of losses from the machine. Weight is what we are looking for. We have specific heat, we have temperature rise. So let's look at the weight. And we said for gases, which is what we are considering here, you would need to use the volume per second over the volume per kg. So how do we make use of that, right? So let's look at the weight of the cooling medium. Right. Now here we make use of Kelvin's law, which says that P1 V1 over T1 at a specific state is equal to P2 V2 over T2 at a specific state for a specific mass. All right. So a certain number of kgs of a gas will have the same ratio of pressure, volume, and temperature in one set of conditions as in the next set of conditions. That ratio remains constant between the two. So what we will do is we will take two conditions, the first condition being normal pressure and temperature, which we can give as the PV over T is normal pressure, let's say 760 millimeters of hydrogen, of mercury, times a given volume, so 1 kg of air at that particular mass, at that particular temperature will be 0.775 kgs, and at ambient temperature of 25 degrees, which is 273. This will be equivalent to the case where we are talking about right now. So here at normal pressure and temperature, NPT, it will be equivalent to this case of ours, whereby our pressure, we have been told, is, I think it is normal air pressure, so it's 760, times, we want to look for the volume of the air, over our temperature, which is 273 plus the rise that takes place. So 273 plus 25. And this will give you the volume for 1 kilogram of air in this particular case, right? This is 1 kilogram that we are looking at. Okay, so we will need to get the volume per kg in order to get VA per second, right? So that 1 kg, let's call this V1, because it will not be the same as VA. Let's call it V1. So that V1 will be equal to 760 times 0.775 over 273 times 273 plus 25 over 760. So these two will cancel out, then we can calculate the two. So V1 is equal to 0.775 times 273 plus 25 divided by 273, and that gives us 0.84597 cubic meters, and this is for 1 kg of air in the specific case that we are talking about. So now if we bring back our equation, so we had Q is equal to Wm times Cp times theta. So Q is equal to Wm times Cp times theta, right? So we know Q we had gotten 906.25. 906.25 is equal to Wm. So now here we are saying Wm, because this is a gas, is equal to a certain volume per second over the volume per kg. So we have the volume per kg. We do not have the volume per second. Let's call that VA, but we do know volume per kg, which we have gotten here, 0.84597 times Cp. Cp was indicated 0.993, 0.993 times theta, which was also indicated as 25 degrees. That's the temperature rise, 25 degrees. So rearranging, we have VA will be equal to 906.25 times 0.84597 divided by 0.993 times 25, which will give us 906.25 divided by 0.993 times 25, which will now be the volume of air that is needed is 30.8826 cubic meters, and that is every second. So every second, in order for us to achieve the cooling that we are required, the amount of cooling air that is required per second in order to achieve a rise of 25 degrees will be 30.8826 cubic meters in every second. Bear in mind that is the amount of air that must pass over the surface. This does not include, so this is not the total air that will be blown onto the machine. It's just the amount of air that will touch the surface. So you can imagine if you need to shift 30 cubic meters per second over the machine, you will have exponentially much more passing through the entire volume of the space that you have. So it is very critical to enclose the machine and be able to direct the airflow in such a way that it is most effective.